Hello everyone, welcome to the course on basic electronics. Myself Umayas. So under module 3 we'll discuss about integrated circuit operational amplifiers and its applications. So in the previous video of this module 3 we discussed about the basics of integrated circuit operational amplifiers, the symbol of the op amp, its construction and the pin diagram of the IC741. So we also discussed about its equivalent circuit and ideal characteristics of the op amp. So now in this video we'll discuss about biasing operational amplifiers and the voltage follower circuits. So coming to the basic op amp circuit. So here the basic circuit of an IC operational amplifier is shown. So the actual op amp internal circuitry is much more complex. The differential amplifier input stage has two inverting and non-inverting high impedance input terminals, and the emitter follower output stage has a low impedance. An intermediate stage between the input and output stages is largely responsible for the op amp high voltage gain. So here in the figure A it shows a BJT input stage, and in figure B it has a FET input stage. Op amps that exclusively use BJTs are termed as bipolar op amps, and those that use a FET input stage with a BJT additional stages are referred to as bi-FET op amps. And some of the important parameters for the 741 IC op amp are listed in the datasheet portion, and that is shown here in this table. So the large signal voltage gain, which is denoted as AV. It is also called as open loop gain, which can also be denoted as AVOL. So for the 741, it is listed as 50,000 minimum and 200,000 typical. So this means that a signal applied as a voltage difference between the two input terminals is amplified by a factor of at least 50,000. So the typical amplification is 200,000 and the maximum amplification can be considerably greater. This is similar to the situation with the HFE of a BJT, where the manufacturer specifies minimum, typical and maximum values. The input bias current, that is I1B, is the base current for the op amp input stage transistors. So I1B is listed as 80 nanoamperes typically, and 500 nanoamperes maximum. So ideally the input stage transistors should be perfectly matched so that zero voltage difference between the two input terminals should produce a zero output voltage. In practice, there is always some difference between the base emitter voltages of the transistors, and this results in an input offset voltage. So that might be as large as 5 millivolts for a 741 op amp. Similarly, because of mismatch of input transistors, there is also an input offset current, which is denoted as IIO, input offset current. So this input offset current is about 20 typical, and the maximum is 5 millivolts. So this, sorry, nanoamperes offset current, 20 to 200 nanoamperes. The input resistance, so this input offset current is a maximum of 200 nanoamperes. The input resistance Ri and the output resistance Ro are the resistances that the op-amp terminals when no feedback is involved. Since virtually all op-amp applications use negative feedback, these quantities are modified in practical circuits. So the DC supply voltage for electronic circuits can vary when the supply current changes, and in some cases there is an AC ripple voltage superimposed on the DC. The supply voltage changes can be passed to the output of an amplifier. Ideally, the supply voltage variations should have no effect on the circuit output, but how good the amplifier is at attenuating supply voltage variations is determined by the power supply voltage rejection ratio, which is also called as PSRR. So this is usually specified in decibel form. Common mode inputs are voltage changes that are applied simultaneously to both input terminals of an operational amplifier. The common mode input voltages can be passed to the output. Common mode rejection ratio, expressed in decibels, defines how good the amplifier is at attenuating common mode input voltages. So coming to the biasing operational amplifiers, like other electronic devices, operational amplifiers must be correctly biased. If there are to function properly, okay, so the inputs of an operational amplifier are the base terminals of the transistors in a differential amplifier. So, and the base currents must flow into these terminals for the transistors to operate. Consequently, the input terminals must be directly connected to suitable DC bias voltage sources. The most appropriate DC bias voltage for op-amp inputs is approximately halfway between the positive and the negative supply voltages. So one of the two input terminals is usually connected in some way to the op-amp output to facilitate negative. So to facilitate the negative feedback. So the connection from output pin number 6 to the connection pin number 2 shows the negative feedback, where a plus or minus supply is used. The other input might be biased directly to ground via a signal source. Base current IB1 flows into the op-amp non-inverting input via the signal source, while IB2 flows from the output into the inverting input as shown. So here the figure or the circuit, one more circuit we have here. This shows a situation in which one input is connected via a resistor R1 to the ground and the other is connected via R2 to the op-amp output, so which is feedback. Once again, base current for the input stage transistors flows into both input terminals. Resistor R1 and R2, resistors R1 and R2 should have equal values so that voltage drops across R1 and R2 will become IB1 R1 and IB2 R2. Approximately, voltage drop across both the resistors will become equal. Any difference in these two voltage drops appears as an op-amp DC input voltage. So this may be amplified to produce a DC offset at the output. So this is the circuit which shows op-amp circuit with one input grounded via resistor R1 and the other input connected to the output via R2. If very small resistance values are selected for R1 and R2 in this circuit, in this figure, then a very small input resistance, that is R1, would be offered to a capacitor coupled signal source. On the other hand, if R1 and R2 are very large, the output voltage drops IB1 R1 and IB2 R2 may be ridiculously high. An acceptable maximum voltage drop across these resistors must be very much smaller than the typical base emitter voltage level for a forward biased base emitter junction. So selecting um, voltage across the R1, which is denoted as VR1, approximately equal to VBE by 10, and R1 max is equal to VR1 by IB max. Therefore, R1 max is equal to VBE by 10 IB max. So in this figure, it shows a voltage divider R1 and R2 providing an input terminal bias voltage derived from the supply voltages. The voltage divider current I2 should be very much larger than the input bias current. This is to ensure that IB has a negligible effect upon the bias voltage. Usually the minimum I2 is selected. I2 of minimum becomes equal to 100 times of IB max. Then R1 and R2 are simply calculated as VR1 by I2 and VR2 by I2 respectively. Resistor R3 in this figure should be approximately equal to R1 parallel to R2 to minimize any difference between IB1 into R1 parallel R2 and IB2 R3 that could act as a DC input voltage. So here we have one problem which shows calculating the maximum resistance for R1 and R2. The circuit is shown in this figure. If 741 op amp is used, determining the suitable resistance for R1, R2 and R3. So this is to give VB is equal to 0 when the supply voltages are plus or minus 15 volts. This is the solution for this problem. So using the formulas and substituting the values to that formula, so we can get the desired values. The IB max is equal to 500 nano amps. So R1 max is equal to VBE by 10 IB max is equal to 0.7 volts. By substituting the value, we get the result for R1 max around 140 kilo ohm. So like 120 kilo ohm resistor can be used, which is a standard value, and choosing R2 is equal to R1 as 120 kilo ohm. Next, second case is like I2 is equal to IB max 100 into 500 nano amperes. So this gives I2 value as 50 microamperes. VR1 is equal to VR2 is equal to 50 volts, and making R1 is equal to R2. So we get the value of around 300 kilo ohm. So that standard of about 270 kilo ohm resistor can be used. R3 is equal to R1 parallel R2. So we get the value for R3 as 135 kilo ohm. Next, coming to voltage follower circuits. Direct coupled voltage follower. The IC operational amplifier can be employed for an infinite variety of applications. So the very simplest application is the direct coupled voltage follower. The terminal output terminal is connected directly to the inverting input terminal. The signal is applied to the non-inverting input and load is directly coupled to the output. So figure B shows the basic op amp circuit connected as a voltage follower. with the differential amplifier input stage. So that equals to V naught, like V2 must equal Vi. When V2 is higher or lower than the Vi, the voltage difference is amplified. To move the output back to equality with the input, suppose V0 were slightly higher than Vi, the voltage at Q2 base would be higher than that at Q1 base. Therefore, IC2 would be increased above its normal level. So this would cause an increase in the voltage drop across RC. This is the basic op-amp circuit connected as a voltage follower. So when there is a voltage drop across RC, thus it reducing VB3 and driving V0 output voltage back to equality with the input voltage. Similarly, when the output voltage is lower than the input voltage, Q2 base voltage is lower than that at Q1 base and IC2 is reduced, thus reducing VRC and increasing VB3 and driving V0 back up toward Vi. This is of course negative feedback. When the input voltage is increased or decreased, the feedback effect causes the output to follow the input almost perfectly. The actual difference between the input and the output voltage is easily calculated from the output voltage level and the op-amp open loop voltage gain. Like an emitter follower, the voltage follower has a high input. So the voltage follower performance is superior to that of the emitter follower. The typical difference between input and output voltage with a voltage follower is only 5 microvolts when the input amplitude is 1 volt. With an emitter follower, there is a 0.7 volt DC voltage difference between input and output. The voltage follower also has a much higher input impedance and a much lower output impedance than the emitter follower. Actual values of Z in and Z out can be calculated from the negative feedback equations, which is derived by assuming certain parameters. So next is capacitor coupled voltage follower. So here we have a circuit for capacitor coupled voltage follower circuit. When a voltage follower is to have capacitor coupled input and output terminals, the non-inverting input must be grounded via a resistor R1. As explained, the resistor is required for passing bias current to the non-inverting input terminal. It also offers an input resistance to the signal source rather than a short circuit. Because the load is capacitor coupled, the DC output offset voltage might seem to be unimportant. However, the DC offset voltage at the op-amp output terminal can limit the amplitude of the AC output voltage. So, a resistor R2 equal to R1 should be included in series with the inverting input terminal to equalize the IB/RB voltage drop and thus minimize output offset voltage. So, designing the capacitor coupled circuit involves the calculation of R1, C1, and C2. So, the circuit impedance, input impedance is R1 is parallel with ZI, that is input impedance. However, ZI is always much larger than R1. So, the circuit input impedance is simply taken as Zin is equal to R1. Normally, the load resistance RL is much smaller than R1, and consequently, the smallest capacitor values are calculated when C2 is selected to set the circuit lower cutoff frequency F1. Therefore, XC2 is equal to Z0 plus RL at F1, XC1 is equal to R1 plus RS by 10 at F1. So this is the discussion about the circuit. So we have the design of the capacitor coupling coupled circuit, which involves the calculation of R1, C1 and C2. The circuit impedance, input impedance is R1 parallel ZI. However, ZI is always much larger than R1, so the circuit input impedance is simply taken as Zin is equal to R1. Normally, the load resistance RL is much smaller R1, and consequently the smallest capacitor values are calculated when C2 is selected to set F1. Therefore, XC2 is written as Z0 plus RL at F1. Capacitor C1 should then be calculated from XC1, Zin plus RS by 10 at F1, so that it has no significant effect on the circuit lower cutoff frequency. Thank you.